Hello everybody, this is Mr. Hennon and I am here to discuss the transfer of heat through conduction. So what we're going to do here is we're going to be looking at how the concept of conduction, thermal conduction affects things. So the thermal conduction, like you already saw from your previous assignment, is the process where we are transferring heat through a material with a bulk motion of the material playing no role. So we're actually, what we're doing is, I love this little statement right here, is the means of little collisions. The more energetic molecules are passing on some of their energies to the less energetic molecules. So basically when you have two materials that are touching each other, if one's more energetic, it's going to bounce around and it's going to transfer some of that to the next one, and so forth. So it's just going to kind of work its way through. So there's a variety of things that affect this. So the first thing you have to have is you have to have a warmer body, so something that's at a high temperature. You have to have a colder body, so you have to have something that's at a low temperature. So one of the things that's definitely going to affect it is the temperature difference between the ends of some material. So whatever that high temperature minus that low temperature is. The next thing that we are actually going to be doing is we're not just looking at the amount of heat that's conducted through it, we're also going to be looking at the time, or we're going to actually be looking at a rate. So as you have heat flowing through something, one of the things you're going to find is the amount of time is going to be important as we're kind of dealing with this. Two other things that come into effect. So the idea is if this is the material we actually have this heat transferring through, there's a couple of other things that are going to affect it. One is going to be the distance from here to here. In other words, between your high temperature and your low temperature. So the actual length of the bar is going to be important. So the length, how much distance it has to travel, which is kind of makes sense because heat is still going to be a flow of something. So the speed or the rate at which is going to happen is going to have a distance. The other one that's important is the cross-sectional area of this. So in other words, if you were to cut out a little slither of this or sliver of this, what would that actually be? So we need to be able to figure out that cross-sectional area. In this particular case, it would be some kind of rectangle or square, and we can kind of look at that. So as I do that, what I put all that together is what things affect the heat and which ones are going to be an inverse relationship. So the amount of heat that's actually going to be traveled, so we're still going to be using Q here to represent our heat, is going to be dependent on a variety of things. One, we have the cross-sectional area, and that's a direct relationship. So the larger the cross-sectional area, the more heat can go through, which makes perfect sense. It's like thinking of this in terms of the flow of anything, whether you think of it as water or something else. So the larger the area you're going to have. The longer the distance it has to travel is actually an inverse relationship. So the farther it has to go, we actually have less heat. So what's happening is that energy, as it's bouncing from material to go through there, it's going to lose a little bit along the way to just random friction with all those particles. So the longer it has to go, the less heat you're going to end up getting. There's a direct relationship between the change in temperature. So if there's a greater difference in temperature between the hot and the cold, you're definitely going to have more heat. If there's a very little temperature difference, then you're going to have less. And then we have the time factor. So the longer you let it run for, obviously, the more heat you're going to actually have go through here. So they have this in terms of this. The last thing is this quantity called the thermal conductivity, which is basically a fancy way of saying what is the material made out of? Is it very conductive or is it very resistive? In electricity, in physics, we often talk about the resistance of materials or the resistivity. But when we're talking about heat flow, we actually talk about the conductivity of that heat. So how conductive it is. So obviously your metals are going to have high thermal conductivities, and your non-metals, your plastics, your insulators are going to have low thermal conductivities. And that's a direct relationship. So the higher the thermal conductivity, the more heat can flow through here. A lot of times we actually bring this T over to the other side, and you'll see this equation written as Q over T, and you'll talk about a heat flow, which this could be written as joules per second, or sometimes it's written as watts, because it's a joule per second is the same thing as a watt. So if you hear a heat flow or the amount of power, so if they talk about heat power, That's another way of relationship. Doesn't really matter which way you do it to me. We'll use both of them. So this is definitely going to be an equation we want to write down. Q equals K A delta T little t all over L. So we can kind of keep all those kind of together. Thermal conductivities can be just something you're going to look up. I put this onto our document so that you can actually use these numbers. Obviously, like I said, the metals have higher thermal conductivities, gases have fairly low, and then other materials down here, some of your insulators like asbestos is an insulator, or goose down, or styrofoam, those are going to have lower thermal conductivities. So if you're trying to transfer heat through there, then you want high ones. If you want to not transfer, then you're going to have low ones. So let's try a little problem. Let's put myself right on top of this thing. So let's say we have excessive heat is being produced within the body. It must be transferred to the skin and dispersed. So if the interior of the body is to stay at 37 degrees Celsius, one possible mechanism for transfer is conduction through body fat. That's going to be important. They gave you back on this page that body fat had a thermal conductivity of 0.2 joules per second meter degree Celsius, a very ugly sounding equation or unit, but that's what we've got. So we've got this K value is 0.2 joules per second meter degree Celsius. I think that's what I had on there. Meters, yep, seconds, meters, degrees Celsius, just making sure. Suppose that the heat travels through 3 centimeters of fat, so that's going to be the length of it that's actually traveling through. My physics alarm goes off, so I don't want to actually leave that in centimeters, so let's make this 0.03 meters. It's reaching the skin, which has a total surface area of 1.7 square meters. So the idea is this is the surface area that's actually going to travel through. So this is going to be my area. It's in the right unit, 1.7 square meters, and a temperature of 34 degrees. So our temperature difference here, we always do high temperature minus low. We're going from 37 degrees to 34 degrees. So we actually have a temperature difference of 3 degrees Celsius as we have this going through. And they want to know how much heat is transferred to the skin in half an hour. Again, my physics alarm should be going off because we don't normally use half an hour. So we'd want to change this into seconds. Remember that there are 60 minutes in an hour, so this is 30 minutes, but I actually want to take 30 times 60 to get that total time. So, or you can say there's 3,600 seconds in 1 hour, so half of that would be 1,800 seconds. So there's our time that we have this. Then from there, we're basically just plugging it into our nice little equation. Q equals K, the thermal conductivity, times the area, times the change in temperature, times the time, all divided by the thickness, or in other words, the length that it's actually traveling through. So I take those numbers, 0.2, take 1.7, take 3 degrees, take my time, this is the large part, so the 1,800, all divided by my length of 0.03 meters. So we're not going through very much, and we should be able to figure out how much total heat. Pull out my handy dandy calculator here. So we got 0.2 times 1.7 times 3 times 1,800 divided by 0.03. And I get 61,200 joules. So this is the total amount of heat that's actually passing through this thing. So this is an example of a thermal conduction problem. We'll do more of these as we kind of get into more of this stuff. I'm just going to stop there, and we'll pick up with a few more notes on thermal conductivity soon. Hope you enjoyed this edition of the Henstitute.